Okay, this video is about how you can actually use Orthohack to generate a customized transform just for your own purposes, whether it be floating point, fixed point, or custom fixed point. And I think the best way to learn this is to look at dct idct8x8 demo.c, which is in the Orthohack demo directory. And by the way, before we start, I mentioned in the previous video that the literalizer outputs a brute force transform. It's only brute force in the sense that it contains no loop instructions. It's not literally multiplying every sample point by every sample point of an ortho basis. So clarify that. But so in this particular file, and by the way, I'm using the lovely LeafPad editor, LeafPad. You can see if you scroll down, you're always going to need this file, orthoconstant.h. That just defines some boring constants. And by the way, generally anything that starts with the prefix ortho in the source code is something that you would potentially include in a deployed product. Whereas the rest of Orthohack, like the preprocessor, of course, does not end up getting included in a published product. So orthodim.h just tells the dimensionality of the numbers that we're dealing with, because at the moment we only support real value transforms. This is 1, but in the future it could be 2 for complex or 4 for quaternion or whatever. And then, yes, of course, the Orthohack file that you generated with the post processor must be included in all cases. Ortho number is purely for floating point transforms. Ortho fixed is for 32.32 fixed. Ortho custom is for 32-bit variable binary point fixed point. By the way, if you include ortho custom, because you're doing a custom fixed point transform, you don't need orthofix.h. If for some weird reason you actually want to execute a literal transform instead of just studying it, you need to include ortholiteral header, and then the actual capture from the literalizer that you generated, and then the footer, which is simply a return instruction. And then finally, we have by 1 and by 8 flavors of floating point, 32.32 fixed, and custom. And generally, you only needed to include one of these. And by the way, you'll notice that in this file, we actually have this notion of transform forward and transform inverse, which are supplied. If you look at the make file, the make script for this demo, it defines forward and inverse successively. So you can potentially use the same piece of code to generate both the forward and inverse transforms merely by including a different Orthohack module. So that's kind of useful. So there are also some operating system calls, but all of this is just to basically print debug output so you can see what the demo is doing. We don't in any way require operating system calls to do any of the transforms. They're designed to be very simple and portable, so that's an advantage versus some other packages. Print 8x8, this simply prints the 8x8 matrix that it's requested in order to produce output. Nothing exciting there. So most of the action is in main. And this is the routine that I recommend you slice and dice in order to figure out exactly how to do the particular type of transform you want to do and nothing else. So the 8x8 DCT literal is the first one. And you can see that we allocate a list of output coefficients. And by the way, we're using this constant here that's from orthohack.h. And likewise here in order to generate the monomial list. And again, the monomials are just the aggregate set of initial sample points and also followed by all of the binomial valuations that were computed. And by the way, the first element of the monomial base is always 0. That's just kind of a guard band thing. You could probably optimize it out at great pains and it would save you hardly any performance. So what we do is we do an init routine, which basically sets the first monomial element to 0. Nothing exciting there. And then one by one, we copy the spatial samples from x, starting at index 0, to the monomial list starting at index 1. And we do that for, in this case, 64 sample indices. Now, you might look at this and say, wait a minute, you're doing it for only 63 because the maximum sample index is 63. Well, it's not. If you look at orthohack.h, the maximum index is 64. The reason is because the first index is always 0, so they're indexed 0 through 64. So actually, this transaction here is in fact copying 64 spatial samples. And then of course we do the transform. And once that's done, we can print out the list of coefficients and free memory. And that's all there is to the literal transform. So the floating point by 1 transform is very similar. And of course, if you do floating point by 1, you don't need to include the literalizer output. We do the same kind of coefficient and monomial list allocation. And we do the same similar init, but of course this is called orthofloat init, not ortholiteral init. We do the same copying of the spatial samples to the monomial list, and we do the transform, and we print it out. That's it. Now, on the by 8, things are a little bit more complicated. We allocate a coefficient list by 8, and this is going to hold the output, and the output format is thus. It's 8 different sets of coefficients corresponding to 8 different transforms, and they're concatenated. So, you know, the first coef count of them are from the first transform, the next coef count are from the next transform, and so on. We also allocate the same thing, but with transposed topology. So basically, the first number in this list corresponds to the first transform, the second number to the second transform, and so on for the first 8. And then we do that again on the second 8, and so forth. So they're all interleaved like that. And this is to make SIMD processing easier whenever we add SIMD support down the road. So then we do the same thing with the monomial list. We allocate it in by 8 topology, and you'll notice the times 8 here for that reason, and that's hard-coded. That's not like 8 by 8 DCT. That's because the transform topology is by 8, okay? And then we do the init, and when we do an init for by 8, as part of that init, the initialization routine actually copies the sample points and interleaves them to the monomial list. So you'll notice that this is a list by 8, whereas this is a by 8 list, so it changes topology. The reason that the by 1 transforms, the initialization routine doesn't do this copy for you and you do it manually is because in reality, you probably wouldn't have to copy. You just simply enter your spatial samples directly into the monomial list. So then we do the by 8 transform, and out pops 8 interleaved, basically a list of by 8 interleaved coefficients. And the last thing we do in a by 8 transform, there's always this end transaction that converts the by 8 list to a list by 8. And then we have a concatenation of complete and full coefficient lists. And we can print those out. Now I happen to choose thread 7 because actually in my demo I do the same transaction 8 wide, the same transform 8 times over, which is obviously silly. In reality you'd have a different transform in every processing lane. So I just randomly select lane 7 and then I free memory. Now for fixed point by 1 and by 8, you're going to find a very similar kind of topology. Basically, I'm sorry, similar code arrangement, right? We're going to allocate a coefficient list. We're going to allocate a monomial list. We're going to copy, we're going to do the init, so ortho fixed init in this case. We're going to copy the spatial samples to the monomial list starting at index 1. But when we do this, we're going to do we're going to convert from floating point to fixed point. Now in reality, if you were to deploy this, you'd probably already have your samples in fixed point, so this wouldn't apply. And then we're going to do the transform, and we're going to convert back. And again, you probably wouldn't do this if you were dealing purely in fixed point. You just stay in fixed point. Print out the results in free memory. And the by 8 is analogous to the by 1, just with the same changes that went into floating point by 8 versus by 1. And you see, of course, the same numerical conversions occurring. So now we can have a look at custom fixed point by 1. This is almost identical to fixed point by 1, except the only thing is we're dealing with customs instead of fixeds. All right, and this, of course, is from orthocustom.h, where these definitions happen. And then on the by 8, we're doing. Oops, I didn't mean to highlight that. On the, see if I can highlight. Yeah, 8 by 8 DCT custom fixed point. There we go. We're doing the same thing as we're doing in by 8 fixed. So. So that is the end of that. I think it's a very valuable exercise to cut up this file and to isolate exactly what it is for the type of transform that you want and nothing else. There is one other thing, which is you need to go into orthohack.h and you can delete, if you're only using the custom list, for example, you can delete the literal list, the number list, and the fixed list, or some other permutation thereof in order to reduce the amount of constant definitions you have. That's it. In the next video, we're going to look in more detail at how the transforms actually work.